this lesson on section 1.2 of our physics textbook, speed, velocity, and position time graphs. Now, the first thing I want us to consider when we're considering just the difference between what speed and velocity is, because probably to this point we've used them as the same term, is consider a track, a racetrack, a running track, anything like that. And consider the fact that we start here on the track, run all the way around the track, and we get back to the end of the track. Well, if we run around that whole track, and let's say that track, just for the sake of simplicity, is 1 kilometer long, and let's suppose it took us 10 minutes to run around the whole track, you would say, well, clearly it's going to, they're on a pace of running 6 kilometers in 1 hour, because there's 10 minutes 6 times in an hour. So 6 kilometers an hour would be their speed. But I would tell you their velocity would actually be 0, because velocity doesn't depend on doesn't matter the path you've taken. Velocity depends only on where you start and where you finish and the time it takes to get from there to there. And so in this case, it's starting and finishing in the same place. So regardless of how much time it takes, your velocity is going to be 0. And so as you can see from the values that I've mentioned here, you can see that distance and speed are scalar quantities. They're what we usually measure things in everyday life in, but physicists are more interested in measuring things in terms of vector quantities. We've already gone over the idea of position, always relative to a point, and displacement relative to a starting point. And so, like I said, if you are displaced 0 meters, if you start here and end here at that point, then your displacement is 0. And because velocity is in meters per second with a direction, and you can see the equation down below here, it's the displacement over the time. So if you have 0 displacement, you have 0 velocity. Now you notice it says AVG, and that stands for, as it says above, average velocity. Because what could have happened over time is you could have, as you're running around that track, you could have sped up at times, you could have slowed down. And so if we're measuring only at certain points, we can just assume the average velocity between those times that we've measured. We can't necessarily account for every single little change in speed that you've had. So speed is change in distance divided by change in time. That's just like what we see going down the road. The speed limit is 80 kilometers an hour or 60 kilometers an hour. The average velocity is this change in displacement. It's this vector quantity that we need to be careful about. And that's also divided by change in time. So clearly time isn't a vector because you can't have a direction with it. So the vector that we're interested in is the displacement. So these are the equations that we're especially interested in this section. And if we rearrange, I'm going to rearrange specifically the velocity equation, the average velocity equation. And I'm just going to keep it as V. I'm not going to write an AVG down there. But if you rearrange that equation for delta D, then we're going to multiply both sides by delta T. And so we would get the displacement as the velocity times the change in time. Likewise, if we were to multiply that by delta T and then divide both sides by V, we would get delta T by itself, and we get the time is the displacement divided by the velocity, the average velocity. And so we're going to have to rearrange that equation at times to solve it. And one of the things that we should do in physics is we should always rearrange the equation before we sub numbers in. I'll say that again. Rearrange the equation before you sub numbers in. All right, so let's look at some questions around this. A boy runs in a straight line for a distance of 50 meters in 8.67 seconds. What is his speed? Well, we're just using that average velocity, but we're going to list or average speed rather. We're going to list the change in distance. The change in distance was 50 meters. The change in time was 8.67 seconds. And the speed is what we're after, is what we're trying to solve. So we know that speed is the change in distance divided by the change in time. So you'll notice I put my given, my required. This is especially important in physics. These questions are going to be relatively straightforward, but we want to get in the practice of using this strategy as we get to things that are more complex. So given, required, analysis, and then we're going to go for the solution. So we're going to sub in 50 meters, and here it doesn't really matter, but when we sub numbers in general, we want to put them in brackets and include the units. So make sure to include units. Because what that shows us is it clearly shows us what units we're going to get in the final answer. So the speed is 50 divided by 8.6, And if my pen will work for me here, the speed is given to be 5.7 meters per second. Now, I haven't clearly defined how many sig digs I have. If it's a 50-meter race, I'm assuming it's to the nearest full meter. So that probably could have better be written as 5.0 times 10 to the 1 meters. That would have been more clear about the sig digs. You could have assumed it was only one sig dig from that number as well. But I'm assuming that it's a 50-meter race. They've probably measured it to at least the nearest meter. And so we'll take 2 sig digs for that answer. And then the last thing we would do for a question like this is a statement. We would write, therefore, his speed is 5.7 meters per second. So that's the process that we're looking for questions in physics to be done as. So let's now look at a question about velocity. The only difference here is that we have this direction added in. Skateboarder rolls 125 meters east in 25 seconds. What is his average velocity? Go ahead and do that equation and then check your answer with me. So have a look at how your answer compares to this. Hopefully you got it right. You'll notice again, I'm listing the givens, listing what I'm required to find. My analysis is listing the equation I'm going to use. My solution is now using that equation to get an answer. And my statement is therefore his average velocity was 5 meters per second. And in physics, we always want to ask ourselves the question, in any calculation question, we want to ask ourselves, does that make sense? 5 meters every second. Okay, that seems about right. If you got 25 meters a second, that's one of the fastest skateboarders I've ever heard of in the world, and you're probably off in left field. So it's good just to make sure, does that seem to make sense in my experience with everyday life? And that should make sense. 5 meters per second is not a bad speed. It's definitely faster than walking or maybe jogging, but it's still a realistic speed. All right, so let's talk about a situation of running across the classroom. So I don't have someone here with me to actually do this, but if we were to have on the ground a line that was 3 meters from the starting point, let's say we start here, and then another line that's 3 meters further away, what this is modeling, what you see in the arrows below, is someone is going to start here, they're going to run 3 meters, they're going to come all the way back, they're going to run 6 meters, and then come all the way back again. So some of you seen this drill used in different sports, but it's just running the lines, touching the lines, and coming on back. So let's pick our friend Phyllis. Phyllis runs across the classroom. We assume that Phyllis, she, has a constant speed, all right? Now, clearly the speed is going to increase when they're changing direction and decrease when they're coming to the end about to change direction again. So it's not necessarily the full picture, but we have to take the average velocities. So we have the vector diagram below of her path, and we're going to label each of the 4 vectors appropriately. Assume that the person runs 3 meters every second. So delta D1, this is 3 meters, and we're saying we're not using north, south, east, and west here. We're using forwards. And so you can see there, I have a clear positive direction labeled. And so I'm going to just label that as F for forwards. And then when they turn around and come back, they're going 3 meters backwards. And then they run 6 meters forwards. And then they run 6 meters backwards. Okay, and so that's what this graph below, it's a scale vector diagram. So 1 meter is represented by 2 centimeters in the diagram. We can draw a position time graph of this. And the position time graph, after 1 second, if they're running at 3 meters per second, is at 3 meters. And then after 2 seconds, running at 3 meters per second the opposite direction, is at 0 meters from the starting point. And then we're running 3 meters per second, so 2 seconds later they get to the 6 meter point. And then again running 3 meters per second means 2 seconds later they get back from the 6 meter point to there. And so what we're going to do on the questions on the back of this handout is we're just going to analyze this briefly. So there's the graph version on the back. And the first question says, calculate the following based on the graph: the average velocity overall and the average speed overall. Well, the average velocity, if you remember, average velocity is the displacement the change in position divided by the time. Well, what's the displacement? Well, the displacement, if you're starting here and ending back at 0, you've had no displacement at all. So even though 6 seconds has passed, you have moved 0 meters, and it doesn't have a direction because you haven't gone anywhere. Your average speed is the change in distance divided by the change in time. In this case, the distance, you've gone 3 meters, back 3 meters, 6 meters, and you've gone 6 meters forward, that's 12 meters, and 6 meters back, you've gone 18 meters in 6 seconds. So what you've done is you've actually moved at a speed of 3 meters per second, though your average velocity is 0 meters per second. I should put per second there. I should have that there. Perfect. All right, so now let's look at going from 0 to 4. So we're going to stop here for this next question. What's the change in distance? Well, the change in distance has been 12 meters. We already counted that, 3 meters there, 3 meters back, and 6 meters forward. What's the displacement? Well, the displacement, you're 6 meters away from where you started, and that is in the forwards direction. What is your average speed? Well, your average speed is, as we already noted, is delta D divided by delta T. So it's 12 meters divided by 4 seconds. Your average speed is in 3 meters per second. Whereas your average velocity, delta D with the line above it, meaning we need the actual displacement, divided by the change in time, that's 6 meters forwards in 4 seconds. So you're 1.5 meters per second forwards. So even though you've gone an average speed of 3 meters per second, your velocity is only half of that. All right, let's look at one more example here. And now we're going to go from 1 to 4 seconds. So we're going to look at 1 to 4 seconds. So here's where we're starting, and we're ending at the 4 second mark. And so let's try to do this on your own, and then you can check your answers with me once you've done that. So you may have done this slightly differently, and I found that a lot of this is intuitive from the graph. But I just wanted to show you as well that these equations that we have work for the change in distance and the displacement as well. The distance that was traveled was 3 meters, and then that was back to the starting point, and then 6 meters back to 6 meters away. And so the change in distance is 9 meters total. The displacement, we started 3 meters at a position of 3 meters forwards, and we ended at a position of 6 meters forwards. And so using that idea of the final position minus initial position, which many of you probably did in your head, you can just say, well, 6 meters forwards minus the 3 meters forwards, which gives you a displacement of 3 meters forwards. And then it's just a matter of using the equations we've done before. So the average velocity is 3 meters per second. The average speed, is 3 meters per second. And the average velocity is only 1 meter per second. And so this is where things get really weird because, and we've seen this a few times now, the average velocity and the average speed are not the same thing. So don't make that mistake anymore, or that assumption as you're describing things. So all the best as you work on those questions today. You'll notice that the homework questions that are listed there aren't the same as the ones that I have on the unit outline. And so feel free to do these ones and challenge yourself with those other ones that are not on the unit outline if you want. But you don't have to do anything beyond this. The main difference is on page 20 here. So I've listed number 1 to 8 on the unit outline. You only need to do 1 to 4 and 7. All the best.